Are you able to see my PPT
Yes, sir.
and my audio is clear to you, na?
Yes, sir, it's clear.
So we were discussing this equation of change and equation of motion. Just I will revise through. So whatever we have covered in last couple of classes. So in first class we have derived the equation of continuity, which will be used in equation of motion. And what is equation of motion is? It is nothing but a generalized shell balance equation. Okay, so we started with some definition. Okay, different types of derivatives and some mathematical input needed for this discussion of equation of continuity, equation of change, or equation of so this whatever mathematical input. So partial time derivatives. So this is when it is constant with location xyz. So here velocity is governed by some other external agency. That time it is called as a total time derivative, and velocity, this is the velocity of system itself. So whatever the system is moving with velocity, if that is the velocity, then it will be a substantial time derivative. Then del operator we have discussed. This is the definition of del operator. So how del is defined in Cartesian coordinate system. So this is in Cartesian coordinate system, and this is in cylindrical coordinate system, and this is spherical coordinate system. And this is how del dot is operated in Cartesian coordinate system. Okay, divergence. Okay, divergence of vector del dot v, del into v. Okay, del into v. This is del into v transpose. Okay, all these operators already we have discussed previously also when we were discussing generalized Newton's law of viscosity. Then we have introduced some more operations of this del. So del into, this is scalar multiplication of del operator with a scalar. Okay, this is the multiplication of del operator with scalar, any scalar. So how it is operated, that we have discussed, and this is commonly termed as del into, and this is del cross. Okay, vector multiplication of del operators. So that cyclic represent to remember, easy to remember, you remember this cycle x y z minus, and this is the reverse of this. Similarly, you can see x y z, this is the cycle. Actually this cycle will move like this. So you can get all this del cross vector. Okay, del cross vector you can obtain very easily. And then some more divergence. Okay, this divergence of a vector. So this divergence of the vector, here we are discussing, it can be anything. Okay, any divergence of any properties. Then vector cross a scalar multiplication of del operator, how it is operated this. And if you are very much interested, so you can go in appendix, all details mathematics is given related to this del operators, and you can go in that. And so that that will be sufficient for you, at least for this transport phenomena subject. And anyway, we are discussing whatever needed, that del operator. This is del square scalar multiplication, that can be represented like del dot del into s. So this will be del to s by del x square, and so on. So with this, with this information, we have started equation of continuity. So equation of continuity. So this is the concept of continuous flow. Flow will be continuous. Simply, what is continuity? Flow will be continuous, and these consequences will be, once there is an interface, interface will be there always. Once there is no interface, interface will not be created in between. That is the consequences. And no segment can be joined or broken apart. Okay, that interface will remains as it is. Then we have derived the continuity equation. This is the mass balance equation, simple mass balance equation without generation and consumption, because in momentum transfer generally we will not consider generation consumption. That will be taken into account in mass transfer actually, if generation and consumption is there. So momentum transfer generally we will look for a fluid without reaction. So generation and consumption is not there, hence equation of continuity without reaction is very useful in momentum balance. Actually with reaction, then we'll go into mass balance. Okay, mass transfer. If there is a generation and consumption, then there will be reaction involved, and then we need to coupled this momentum transfer with mass transfer also. But currently we are discussing purely momentum transfer. So momentum transfer will be just without any this thing generation and consumption. So differential element is considered delta x, delta y, delta z. Then mass flux is considered. Okay, mass flux into surface area. This will be velocity. Velocity into density will be a mass flux, and mass flux multiplied by surface area will give you rate of mass coming in. So you can get rate of mass coming in x direction. This will give you rate of mass going out in x direction. Similarly, so this will be a flux multiplied by surface area. So flux multiplied by surface area. This will be rate of mass coming in this differential area in x direction, and this will be a rate of mass going out in x direction. Similarly, for y direction and z direction, and the rate of increase in mass, that will be accumulation of mass. So how this mass, okay, mass will change in this differential element, that I can get volume multiplied by density. So volume multiplied by density will give you mass, and d by dt of this will give you rate of increase of mass. Rearranging all this equation for y direction, and this will be a accumulation of mass. This term will give you accumulation of mass. Rearranging all these equation and dividing this equation by delta x, delta y, delta z, and delta x, delta y, delta z tends to 0, and using the definition of differential equations. So we'll be getting this equation. This is the first form of equation of continuity. So this can be written in short form, compact form, not short form, compact form you can say. So d rho by dt equals to minus del dot rho v, the divergence of rho v. So this is divergence of rho v, and then we have used many a times a simplified form of, or a special form of this continuity equation for incompressible fluid. Incompressible fluid means constant density system. Constant density system means d rho by dt will be 0, and this rho can be taken out. So del dot v will be equals to 0. So this equation we have used, uh, I think almost in all the problems uh, in shell balance equation, and in first chapter also. So when we were discussing generalized Newton's law of viscosity, that time we have used here. So hence, because of this only, because we are handling most of the time liquids and liquids and incompressible fluid, so this will be equal to 0, and only first bracket you consider in most of the time. So this is equation of continuity, and then we have discussed a different form of equation of continuity. This is one form of equation of continuity, and this is another form of equation of continuity. This is just, you can open up this density into velocity, and this is considered as a one function. This is considered another function, and rearranging this equation and using the substantial time derivative definition, so I can get this equation. This is what we have done. So this is another form of equation of continuity. So more details about this, you can get this equation. These are the equation for Cartesian coordinate system. This is the equation for cylindrical coordinate system. This is the equation for spherical coordinate system. You can, as we have derived this equation, you can similarly you can derive this equation, or what you can do is you can use this equation, you can use this
Excuse me, sir.
equation and use the definition of substantial time derivative for yeah, tell me.
Sir, your voice is breaking actually. We are not able to understand.
Yeah, anybody have any doubt?
Sir, your voice is breaking.
Now it is clear.
Not
Now it
that
is
much, sir.
coming properly. Okay, just
Yes,
hold
sir.
on. Now, are you able to listen properly?
No, sir, it's still breaking.
Still breaking. So there is no problem from my side actually. It is internet is also full. Everybody is facing same problem.
Yes, sir. At the start, it was breaking, sir. Now it's somewhat clear.
Can you
Sir, we
write
can
in chat
adjust
box?
as of now. Maybe you can continue. If it breaks more, then we'll tell you.
Yeah, yeah. Can you write in chat box how many of you are getting problem? Now also you are getting problem, or now it is clear?
Now it is clear, sir.
Okay. Okay. Anyway, I will continue, and maybe if you are getting a problem, so you can tell me. Can you see my PPT?
Yes, sir.
Okay. So this is what continued equation we have discussed. So what I told is these are all three continuity equation. So one is for Cartesian coordinate system, another is for cylindrical coordinate system, third is for spherical coordinate system. We have derived this equation. Similarly, you can derive this equation and this equation also. But another way to get this equation, for example, for cylindrical coordinate system and spherical coordinate system, is using this compact form of this equation. Now I have this compact form of this equation of continuity. This is true for Cartesian coordinate system, this is true for cylindrical coordinate system, and this is true for spherical coordinate system also. Only the thing is, the substantial time derivative, you need to use the definition in cylindrical coordinate system. Similarly, you need to use del as defined for cylindrical coordinate system. If you use that definition, how del dot is operated, you operate this, so you can get the equation in cylindrical coordinate system also. Okay, that is the beauty of writing equation in compact form. So you can say you can get a generalized equation first of all, and using that generalized equation you can get whatever this complicated equation for cylindrical coordinate system also and spherical coordinate system also. That is the beauty of this thing. And then we have started the discussion on equation of motion. So as I told, this equation of motion is nothing but the generalized shell balance equation, without considering anything. So without considering anything, so I am not considering steady state also. So accumulation term is also there. Rate of momentum is there. Rate of momentum out is there. For all three momentum. For all three momentum means I will get a three equation. First will be for x momentum, y momentum, and z momentum three. And this total forces acting in that direction actually. Whatever be the gravitational force, most of the time gravitational force will be the external force acting on a fluid. So rearranging this equation, so this is for x momentum. So this is x component of x momentum, this is y component of x momentum, and this is z component of x momentum. So flux multiplied by surface area will give you rate. So this will give you rate coming in. This 3 will give me a rate coming in, and this 3 will give me a rate going out, and total forces. And this is for x momentum. This is for x momentum. So this will be a rate coming in minus rate going out, rate coming in minus rate going out, rate of momentum coming in, and this will be a total forces acting. And accumulation will be a how this momentum is accumulated. Here I am taking momentum balance equation. Okay, shell balance for momentum transfer. So momentum, x momentum, rho into velocity will be x momentum, and multiplied by a volume and divided by time. That will divided by time, that will give me accumulation. So rearranging, dividing it by delta x, delta y, delta j, and rearranging the equation, we got this equation. This is the x shell balance for x momentum. Shell balance for x momentum. Similarly, we'll get shell balance for y momentum, shell balance for z momentum, and this in compact mathematical form, this will be divergence of total momentum flux into rho into gravitational force in that direction. So I can be varies from xyz or r theta phi, and accordingly, so you can get the equation for cylindrical coordinate and this thing. This is again generalized equation. So substituting the definition of total flux, which consists of convective flux plus molecular momentum flux. So this is the first form of equation of change. This is called as a accumulation term. This is called accumulation term. This is called as a convective term, as we know that this is convection. Okay, convective momentum flux. So this is convective flux. This is pressure flux. This is viscous flux, the viscous term, and this is the gravitational term. So this is first form of equation of change. So this
Hello, sir.
then we can tell me.
Sir, gravity won't be acting in all three directions. No, sir.
Yeah, it will be there, na? Gx, Gy, Gz.
Sir, only in negative z direction.
If say my gravitational is not parallel to any of the axis, then there will be x component of gravity, y component of gravity, z component of gravity. If say my gravitational force is parallel to x axis, then Gy, Gz will be equals to 0. Okay?
Yes, sir.
But say if my gravitational force is not parallel to any of the axis, okay, it is not in any of the axial direction, then there will be 3 component of the gravity.
Yes, sir. Yes.
Okay,
Yes, sir.
got it?
Yes, I got it, sir.
Okay. So this is the equation. So this is a form of the equation. And then this is the definition of total flux, and this is the substantial time derivatives definition. And this is the definition of divergence of property. Combining this, so we can derive this equation. So here density is not constant. That you need to remember. This is also generalized equation. This is first form of generalized equation. This is second form of generalized equation. This is also density is not constant in this equation. In fact, continuity equation is used here. So once you got this equation using the substantial time derivative and divergence of property definition, so you can write the compact. So this is also generalized shell balance equation. Okay, this is not a special case or some you can say special case, or this is generalized equation applied for variable density also. Even though it looks density outside this differential, but this is rearranged, and so that is important point to note. So how to get this equation? So just substituting all these definition and opening up the bracket and using the definition of product rule. How product rule is applied in differentiation and rearranging. So this is here we got RHS. So then LHS is also rearranged. LHS rearranged. So RHS we got, LHS is rearranged. Then after rearranging this LHS, also here you will get, okay, this equals to 0. Okay, this equals to 0. You can see this is the continuity equation. This is continuity equation, generalized continuity equation, and this equals to 0. This already we have proved just in previous class, or just now also we have discussed this continuity. As this is equals to 0, so this LHS will be equals to this, and then this is continuity equation. Substituting this, LHS will be this actually. LHS, and hence LHS and RHS both are proved. Hence I can write, I got this equation. Okay, this is generalized equation, and then using the definition of substantial time derivative and divergence of the property, this equation can be written in the compact form like this. Okay,
So these are the Cartesian coordinate system, x momentum, y momentum. Similarly, I can get for y momentum, and similarly I can get for z momentum for Cartesian coordinate system. Now that is the beauty actually for mathematics. I can write this in compact form and get the equation for y momentum, z momentum, cylindrical coordinates, Cartesian, spherical coordinate, and so on. Okay, so this is this is the equation of change for cylindrical coordinate system, r equation of change, theta equation of change, and z equation of change, or r equation of motion, theta equation of motion, and z equation of motion. This is all equation of motion, generalized equation. Okay, this is generalized equation. Then for special case, for constant density and viscosity, generally in chemical engineering, most of the problem dealt with a liquid. In momentum transfer, here we are discussing momentum transfer. So most of the momentum transfer in chemical engineering is dealing with a liquid. So liquids are generally assumed to be having a constant density, incompressible, and constant viscosity also. Most of the 80% of the problem in chemical engineering will deal with. So we can rearrange this equation so that we'll get a simplified form of equation of motion. Okay, equation of motion. So this viscosity can be taken out from here, and we will get a velocity directly, Navier-Stokes equation. This is called as a Navier-Stokes equation. This is Navier-Stokes equation for x equation of motion, and this is what a Navier-Stokes equation. Okay, compact form of Navier-Stokes equation. Here density is also constant, viscosity is also constant. Okay, compact form of Navier-Stokes equation minus, this is pressure term, this is, you can say, viscous term, and this is a gravity term actually, and this is the accumulation term. This is accumulation term or substantial time derivative of velocity. So, and this is a combined pressure form. So this is Navier-Stokes equation, pressure and gravity. Okay, this gravity is also kind of potential head, and this is pressure head. This, if we combine together, this is combined pressure form of Navier-Stokes equation. So this is general form of equation. First form, we got first general form of equation of motion. Then after rearranging, so after for constant density and viscosity, this is the Navier-Stokes equation. This is Navier-Stokes equation, and then we have constant density, viscosity, combined pressure form. So this is the equation. Then we have non-accelerating flow. Non-accelerating flow means this will be equals to 0. If acceleration is 0, this will be equals to 0, and constant density and viscosity. So this is the equation we will get. This will be equals to 0 for non-accelerating flow. So this negligible viscous forces. Sometimes viscosity of the fluid is very, very low. So this term will be negligible. This contribution of this term will be negligible. So we can get this. So altogether, these are the 5 different form of equation of change. This is generalized form of equation of change. Okay, general form of equation of change. This is subjected to constant density and viscosity. This is subjected to constant density, viscosity, and combined pressure form. This is for non-accelerating flow, constant density and viscosity, and this is for negligible viscous flow. So these 5 equation, if you remember, so again I am telling, this is the beauty of mathematics. So in mathematics, you can write all the equation in compact form. Now compactly, I have written all the equation in compact nature using mathematics. Mathematics means I am using a definition of this substantial time derivative, a del I am using, del dot I am using, del square I am using, here also del into I am using, all these operators I am using. So all together, this general form of equation of change, using this one equation, you can get almost 9 equation, not almost, you can get 9 equation. What are these 9 equation? First of all, you can get 3 equation in Cartesian coordinate system, 3 equation in cylindrical coordinate system, 3 equation in spherical coordinate system. In Cartesian coordinate system, one equation will be for x momentum, y momentum, and z momentum. In cylindrical coordinate, you can get r momentum, theta momentum and z momentum equation. In spherical coordinate system, you can get r momentum, theta momentum, and phi momentum equation of change. Okay, so this one equation, using this one equation, if you remember the definition of substantial time derivative del for cylindrical coordinate, Cartesian coordinate, and spherical coordinate, you need not to remember all these 9 equations. You can just remember this compact nature of the equation, and you can get all these 9 equations, and accordingly which equation is required, where which equation is required, you can get back that equation and try to solve for equation getting velocity profile, and then you can get all the properties. Similarly, these also equation represent almost 9 equations. So even though on a slide these are only 5 equations, altogether these are not 5 equations. These are a 9 into 5, 45 equation of change. Okay, now 45 equation of change. So out of which 15 will be for Cartesian coordinate system, 15 will be cylindrical coordinate system, and 15 will be for spherical coordinate system. So, and you will not be needing these 45 equations all the time, but you need to remember all these 45 equations. You don't know what is situation, which problem you are encountering, whether it is general form, constant density form, constant viscosity form, combined pressure form. So any one equation only you will be needing in future for solution, but altogether you will start with this 45 equation. So these are the 45. So this you can see only this is Navier-Stokes equation. This one equation, okay, this is same equation. This is same Navier-Stokes equation for Cartesian coordinate system. Now using this definition of substantial time derivative del into and del square, so you can get this equation. Okay, you can get this equation. So this is Cartesian coordinate system, equation of change, 3 equations: x equation of motion, y equation of motion, and z equation of motion. So this is written in compact form, this second equation. Okay, so this is Cartesian coordinate system. Similarly, you can get back for cylindrical coordinate system. So this will be for r equation of motion, theta equation of motion, and z equation of motion. Okay, and similarly you can get back this Navier-Stokes equation for cylindrical coordinate system, r equation of motion, theta equation of motion, and z equation of motion. So these are 9 equations. Okay, these are 3 for cylindrical coordinate, 3 for spherical coordinate, and 3 for Cartesian coordinate system. All together, these 9 equations compactly can be written in this equation, this second equation. So second equation is more than sufficient. Okay, second equation is more than sufficient, and everything compactly can be written in this equation. Similarly, you can get 9 equation from the general form, 9 equation from this form, 9 equation from this form, and this 45 equation. So whichever equation is needed, so you can write that equation, start the derivation, and get the velocity profile. Then you can get appropriate different design important properties. Okay, so this is what we have discussed in previous class. Anybody has any doubt? Am I audible?
Yes, sir.
Okay, so no doubt. So this is just a revision, very important. Now we are going to apply this equation of change. So first we'll discuss flow through pipe. Okay, so flow through pipe, I'm going to revise what we have done in this flow through pipe. So we have solved this problem in a class using shell balance approach. Same problem now we are going to solve using equation of change approach also. Okay, so just I will revise what we have done. This is exactly similar what we have done. So just I am revising what we have done first, and then we'll see how same problem can be solved for using equation of change approach. Okay, so this is the flow through pipe. So there is downward flow. So and this is shell we have considered. Okay, this is just I am revising what we have done previously. Okay, then we will go to shell balance. So this was the shell of delta r thickness. So rate of momentum coming in, rate of momentum going out, rearranging all these equation and writing in combined pressure form. So we got this equation. Okay. So this is the you can say a definition of generalized Newton's law of viscosity. So this is combined pressure form. So we have written P0 plus rho g, P0 plus rho g, P0 minus rho g, because this is moment is in downward direction. So this is combined pressure form. So integrating this equation and using logical boundary conditions, so we got this is the flux profile. And then we have used generalized Newton's law of viscosity. Newton's law of viscosity, and introducing this Newton's law of viscosity, integrating this and substituting a boundary condition. So we got a velocity profile. This is what we have done previously. Now we'll be solving same problem. Okay, this is my velocity profile. This is my flux profile. So anyway, this equation is not going to change. If you get by generalized shell balance equation or a simplified shell balance equation, you will be getting same equation you will be getting. Only this is the another way to solve the problem. So what equation of motion is just a generalized shell balance equation. Then we'll add all the assumption. So here what we have done in previously in chapter number 2. So we have added all the assumption and defined the shell, simplified, and we have operated a shell balance for one directional flow, one directional variation. But that will not do in equation of change. Equation of change is the generalized equation, shell balance equation. Then we'll add all the assumption. Okay. So, and this is what property we got. Now we will solve same problem using this equation of change. Okay, equation of change. Now, how many equation of change we have? How many equation of change we have? Roll number 41, Mithilesh. Roll number 41, Mithilesh. Roll number 42, Rishikesh. Am I audible?
Sir. Yes, sir.
It's 41, 42. 43, Akash.
Yes, sir.
So how many equation of change we have all together? What is discussed in a 45 equation of change. So these are the 45 equation of change. Now Akash, so this is the problem. So hope you might this problem was given to you in last class at the end also. So you got this is constant density viscosity system. So which equation you want to use out of this 45? First, second, 3, 4, 5. Which equation is useful here?
Constant pressure and second equation maybe.
Okay, most of the time. Okay, this I have given told you initially also, most of the time, as
Papa.
here in this.
Sorry, sir.
So as I told initially also, most of the problem in chemical engineering, momentum transfer will be dealing with a constant density and viscosity system. So this second equation is useful. Now from this 45 equation, we have boiled down to only 9 equations. These 9 equations will be useful for us. Now Narendra, roll number 44.
Yes, sir.
So what are these 9 equations which is represented by this second equation on the slide?
Three are cylindrical, sir. Three are spherical, and remains.
Three are
Three are spherical, sir.
three are spherical, three are cylindrical, and three are
Cartesian.
Cartesian coordinate system. So
Yes,
now from this 45, we have reduced to 9 equation. Out of these 9, 3 equation will be useful. Which 3 equations are useful? Narendra?
Yes, sir.
So which 3 equation will be useful?
We'll take cylindrical, sir.
Why? Yes, because this is flow through pipes. Now this is how you need to eliminate the equations. Which equations are useful? So these are 45 equation. So given was constant density and viscosity form. Hence we are using this equation. This is Navier-Stokes equation. So there will be 3 Navier-Stokes equation for cylindrical, 3 Navier-Stokes equation for Cartesian, and 3 Navier-Stokes equation for spherical. Now we are dealing with flow through pipe, and which will be solved by cylindrical coordinate system. Hence 3 Navier-Stokes equation for cylindrical coordinate system will be useful. Okay, out of these 3, which will give me velocity profile? Roll number 45, Prabodh. 45, yeah. Not able to listen to you. 45.
Yes, sir. Am I audible? Hello.
Roll number 46, Aishwarya.
Yes, sir.
So this 3 cylindrical coordinate system, what are these 3 equation first of all?
For X, for Y, and for YZ. Sir.
How XYZ is in 3 cylindrical coordinate system?
Sorry, sir. R, Z, theta, sir.
R, Z, theta. So R equation of change will give me a velocity profile. Z equation of change will give me a velocity profile, or theta equation of change will give me a velocity profile.
Z, sir.
Z, why?
Because for R and effects are neglected, and for theta due to symmetrical from every
Yeah,
side.
there is no velocity in R direction. There is no velocity in theta direction. There is a velocity only in Z direction. Hence, Z equation of change cylindrical coordinate system will be used to get the velocity profile equation. So,
Yes.
so now we have reduced this 45 equation to one equation, single equation, which will be used to calculate the velocity profile. So if you are wrong in selecting the equation, either you will end up with complicated mathematics.
Yes, sir.
Are you able to listen to me?
Yes, sir.
Okay. Because of these wrong assumptions, so you will end up with either complicated mathematics or wrong answer. So this selecting that single equation is also very important based on given problem. So this is the given problem because this is flow through circular pipe. So cylindrical coordinate system, constant density and viscosity. So Navier-Stokes equation and flow through circular pipe, and you can say gravity, consider a steady state laminar flow is there. Laminar flow means 1D flow, one dimensional flow. So no velocity in theta direction, no velocity in R direction. Z equation of change or Navier-Stokes equation, Z equation of change will be used to get this velocity profile, and then using this velocity profile you can get flux profile, and you can get all design important property in momentum transfer. Actually, this is how you need to solve the problem whenever you are using equation of change. So you will be starting the problem with all 45 equation, then reduce down to 9 equation, then reduce down to 3 equation, and then reduce down to 1 equation, which is important. Sometimes you will get Vx, Vy, Vz. So all you need to solve all 3 equations simultaneously. You need to solve all 3 equations simultaneously. Maybe sometime you will get a different information from different equation of change. Okay, so this is the cylindrical coordinate Navier-Stokes equation will be used. So this is the expanded form of this equation, expanded form of this equation in cylindrical coordinate. So this is R equation of change, theta equation of change, and Z equation of change. As we don't have velocity in r direction, we don't have velocity in theta direction, so certainly this will not be useful for us. So this will not be useful for us. Okay, and then that is what this. Now once you got this equation, so you need to take out all the information. Now take out all the information. What are these informations available? So pressure is a function of z, and v theta is a function of r. So something what is given on slide, roll number 47, Gurupreet.
Yes, sir.
Yeah, is it correct or wrong?
Sir, I guess Vz will be V theta will be 0, and we have velocity in the Z direction.
Very good. So what is this is wrongly mentioned in intentionally actually, so that just to know that whether you are in a class or somewhere else. Okay, so this is what. Okay, so pressure is a function of z. This is first of all because of gravity and external agencies also. Okay, this is written in the form of combined pressure form. Okay, this is combined pressure. This pressure have a gravitational effect, gravity effect, plus whatever be the external agency, and Vz is a function of r. So these are the two boundary conditions. So pressure should be given initially and at the end, and at r equals to r, velocity is 0. This is no slip boundary condition. These are the three boundary conditions available, okay, as of in given problem. So when we are applying Navier-Stokes equation to solve the velocity profile, so you can get this information. You are taken out this information from the given problem. Now applied to Navier-Stokes equation. Now applied to Navier-Stokes equation. So this R equation of change is not useful because we don't have velocity in R direction. Theta equation of change is not useful because we don't have velocity in theta direction. Only Z equation of motion will be useful to get the velocity profile. Okay, Z equation of change is useful. Okay, now using the Z equation of change, you need to eliminate term one by one, whether this is 0 or non-zero, this is 0 or non-zero, and see. So all collect only non-zero term. So
Excuse me, sir.
tell me.
Sir, in the different form of equation, we have 5 equations. Sir, why we are using second one? Sir, we should use fourth one.
Yeah, that you can do.
Because sir, our flow is non-accelerating. We have constant velocity in Z
So
direction.
anyway, if you use second also, that you will get same equation ultimately. So this is you can say 80% of the problem in chemical engineering, you can start with a Navier-Stokes equation. That is one intention why we are using equation number 2. Ultimately, it will be same. So when we will analyze this equation, we will boil down to a fourth equation only. Okay, you will see now. See, after simplifying this, roll number 49.
Yes, sir.
Roll number 49.
Yes, sir.
So can you see my arrow?
Yes, sir.
Can you see my arrow in a screen on a screen?
Yes, sir.
So whether this term is 0 or non-zero?
This one will be non-zero because we have velocity in z direction.
And what is this?
It's varying with. Okay, so that will be zero because it's not varying with time.
Why?
Vz
Why?
will be constant. In z direction, Vz will be constant.
Okay.
Variation with time will be zero.
With the time, where it is given?
Potential is taken with respect to time. That is why.
Yeah, where it is given in a problem. Whether it is given in a problem somewhere.
So steady state.
Very good. So it is steady state. Just now it was discussed. The minute before it was discussed, same thing was discussed, only language was something different. Somebody was telling that it is non-accelerating flow. And now it is steady state. One and same thing. So this telling that it is non-accelerating flow for closed pipe and telling that it is steady state. So that is one and same thing. Okay. So roll number 50, Rashmi.
Yes, sir.
Whether this is 0 or non-zero.
Sir, it is no. Vz is varying in r direction. So it so Vz is sir, it will be non-zero because it is varying in r direction.
Where is my cursor? Can you spell out? Can you tell me what term I am indicating on a screen?
dvz by dr.
So this is only dvz by dr or something else is there with that term?
Yes, sir. So Vr is 0, sir. So that's why the whole term is 0.
So whether this term will be 0 or non-zero?
0, sir.
0. What about this term?
So the whole thing will be 0, sir, because V theta is 0.
Very good. What about this term?
So this will be non-zero.
This will be non-zero. This will be 0 or non-zero?
So Vz is non-zero. So Vz by dz is 0. So total term will be 0. So because it is not a function of z, like Vz is not a function of z.
So this whole term on left hand side will be equal to 0. This is what happened in non-accelerating flow. Okay, so if you take fourth equation, if you understood properly, okay, then actually, so straight away you can use fourth equation in that list. Okay, so got the point? Okay, somebody was pointing out, na?
Yes, I got it.
Okay, so this whole term is 0 actually. So after analyzing, so ultimately what you will get, whole term equals to 0. Roll number 51, Himanshu.
Yes, sir.
What about this term?
So non-zero, sir. dp by d.
Okay. Why it is non-zero?
So pressure is changing in relation to z. At z is equal to 0, pressure is P0 and z is equal to L, pressure is PR.
Okay. And this flow is there because of the pressure difference only. So pressure
Yes, sir,
is
the flow
changing
is
in
there.
z direction. So this is non-zero. How about this term?
So this term is non-zero, sir.
0 or
Non-zero,
non-zero?
sir. Non-zero.
Why?
So Vz is function of R. Vz is changing and then R is changing
Vz is
from origin.
Vz is changing in r direction. You can say here also it is d by dr. Here also it is d by dr. And this is Vz. So this equation is a variation of Vz with respect to r. Hence this is non-zero. How about this term?
Sir, 0, sir.
0. How
Next
about
one.
this term? Why this is 0?
Dz is not function of theta, sir. Symmetry, sir.
Very good. Symmetry. How about this?
Sir, 0, sir. Dz is not changing in
0.
the situation.
Why?
Steady state, sir.
No, this is not a reason actually. Wrong reason. Vz is not function of z. This is due to steady state.
Continuity equation.
Continuity equation. Okay, continuous flow. Continuous flow, closed flow, non-accelerating flow. Okay. It is not because of what you told initially. What
Steady
reason
state,
you go?
sir.
Yeah. Steady state. So
Yes,
it
sir.
is not because of steady state. Okay.
Okay,
And
sir.
whether this will be 0 or non-zero.
So non-zero, sir. Parallel to the z
So
direction.
so GZ. So GZ will be now this. You need to know whether you are considering z axis in a direction of flow or opposite of the flow. So that will decide the direction of GZ. GZ will be equals to either plus G or minus G. Here G, gravitational force, is in the direction of flow, so it will be plus
Plus
of
G,
G. Okay, plus G. So you can see this. This is not important equation because this is our equation of change. This is theta equation of change. This is important equation. Everything is 0. This is non-zero term. This is non-zero term, and this is non-zero term. Okay, so this one equation will. This is the simplified equation. Now only the thing is, now we need to solve this differential equation. So now you can see this is multivariable differential equation. So this is multivariable differential equation, and this can be written in, you can say, a combined pressure form. This can be written in combined pressure form. This can be combined together. Okay. Yeah. Anybody has any doubt?
ఫంక్షన్ కి లూజ్ ఉంటుంది కొంచెం బాగుంటుంది ఫిట్ గా పాత చొక్కాల నేను వేసుకోవట్లేదు సరిగ్గా పాత వేసుకోవట్లేదు
Okay, this is combined pressure form. So this is multi-parameter, multi-variable. Pressure is also variable. Z is also variable. Vz is also variable. Okay, this is multi-variable differential equation. So you might have consider many methods to solve this problem. So you can solve using any of the method. So one method is, okay, and these are the 3 boundary conditions. So 3 boundary conditions. Certainly one more boundary conditions is needed. So we'll see what will be that boundary condition. So how to solve this problem? So this will be, so rearranging this equation. This equals to 0. So this variable differential equation with respect to velocity will be equals to del p by del z, and can be taken that equals to some constant. Any constant you can take. Okay, any constant you can take, and you can solve this differently, and then combine the form, actually combine the equation. So solving this for velocity, okay, so this is the equation. So solving this for velocity, del p by del z equals to c0, and using this 2 pressure, okay, and this equals to c0, and using this P equals to C0 Z bar plus C1, and I have 2 boundary conditions for pressure actually. 2 boundary conditions are at Z equals to 0, P equals to P0, at Z equals to L, P equals to PL. So I can get the value of C0 and C1. So what is the value of C0 and C1? So solving this, del P by del Z equals to C0, one constant, and integrating this equation. So pressure will be equals to C0 Z plus C1. So, and these are the 2 boundary condition. At Z equals to 0, P equals to P0. At Z equals to L, P equals to PL. What is the value of C0 and C1? Roll number 52, Spandan. Roll number 52.
Hello, sir. Hello, sir.
Spandam.
Yes, sir.
Tell me.
Sir, C1 will be P naught.
C1 will be P naught.
P naught.
And C0 will be?
C0 will be P minus P naught by L.
P minus P naught by L. So C naught is P0 minus P naught, or PL minus P naught by L.
PL, sir. Sir, PL.
What is C1 equals C0 equals to?
Yes, sorry, sir.
What is C naught equals to?
Sir, C naught equals to PL minus P naught by L.
Very good. PL minus P naught by L. And now integrating this equation, what you will get? You need to integrate twice this equation. So you will get this equation. So Vz will be equals to C naught divided by 4 mu L R square plus C2 ln R plus C3. Now C naught is already estimated. C naught is PL minus P naught divided by L. To estimate C2 and C3, I need two boundary condition for velocity, but there is only one boundary condition for velocity. What will be another boundary condition for velocity? Anybody in a class? So got the point? Roll number 53.
Hello. Yes, sir.
Yeah.
Sir,
So how to get this C2 and C3? How many boundary conditions are needed?
sir,
Now
two
this
boundary
velocity
conditions are
profile
needed.
equation has three constants: C naught, C2, and C3. C
Yes, sir.
naught is already estimated.
Yes,
Now
sir.
C2 and C3, how many boundary conditions are needed?
Two boundary conditions, sir.
So one boundary conditions for velocity is given at r equals
Yes,
to
sir.
capital R, Vz equals to 0. This is no slip boundary condition. What will be another boundary condition?
Sir, at the center of the tube, the velocity will be maximum, like at r equal to 0.
At r equals to 0, velocity will be maximum.
Yes, sir.
So you need to put Vmax.
Yes, sir.
So what will be ln 0?
Oh, that will be undefined, sir.
At r equals to 0, what will be ln 0 equals to?
Not defined, sir. Ln r will be not defined.
So how to handle that?
Then we
That
can.
logical boundary condition we will use. At r equals to 0, velocity is a finite, okay, finite value. Velocity
Yes,
has
sir.
finite value at r equals to 0. Hence, this C2 should not be there in my equation.
Yes, sir.
At r equals to 0, I have my system. But at r equals to 0, ln r will be undefined. So I cannot have undefined velocity at r equals to 0. So this term should not be there. So
Yes,
this
sir.
term will be eliminated. C2 will be eliminated using this boundary condition. Which boundary condition?
At r equal to 0, Vz is finite.
At r equals to 0, Vz is finite. Okay, at r equals to 0, Vz is finite. So C2 should not be there. C2 should not be there. And C0 is equals to PL minus P0 divided by L. So I'm using this boundary condition at r equals to capital R. So Vz equals to 0. Substituting this, I can get C3. Substitute this C3 and rearrange the equation. So you will be getting this equation. Okay, Vz will be equals to P0 minus PL divided by 4 mu L into R square 1 minus R by R whole square. This will be the velocity profile. Get the value of C3 and rearrange the equation. So you will be getting this profile equation.
Yes, sir.
So just write in a chat box how many of you are getting this equation. So get the value of C3, C0 we got, C1 we got, C2 you can call it as a 0 or C2 should not be there. That C2 Lanar term should not be there in my model equation, logical boundary condition, that is called as a logical boundary condition. Logically C2 is eliminated and C3 you can estimate using a no slip boundary condition. Substitute this C0 and C3 and rearrange the equation, you will get the velocity profile equation. Okay, many people got it. Anybody is not getting this equation? Everybody got this equation? Only few people have written in chat box. Are you writing your notes or just listening to class? Your roll number 86, Prashant. Yes is for writing notes or you got the equation?
Yes, sir. I got the equation, sir.
Okay, very good.
Yes.
So you can see this is the same equation. This is same equation which we got. So this is so equation of change is not you can say very different from shell balance equation. This is generalized shell balance equation. We got a generalized shell balance equation, that is Navier-Stokes equation or general form or whatever it is. So we'll select that equation and substitute all the assumption in that and then solve for velocity profile. Okay. So now take down this problem. This is very, very important problem actually. So very, very important problem. Take down this problem and draw the figure properly. Take out all the information available in this problem. This is angular velocity omega 0 is given. Okay, radian per unit time. This is angular velocity. So how to get a linear velocity using this angular velocity? Anybody in a class? V theta is a linear velocity. Omega 0 is an angular velocity. How to get how this omega 0 and V theta is related?
Omega is equal to V by R.
Very good. Omega equals to V by R. R will be the radius of rotation. Okay, radius of rotation. So whatever be the wherever you are considering radius of rotation, accordingly that V theta will be calculated. V theta will be equals to omega into R. Okay, linear velocity and angular velocity. Now write this problem carefully, draw a figure properly and take out all the information as we have done in for cylindrical system. Actually, cylinder flow through pipe. Okay, flow through pipe. Take out all the information and then just see out of 45 equation which three equations are important. Out of this three equation, which equation will give me a velocity profile equation? That you need to think properly, and then we'll be discussing the solution of this problem. Okay, write the problem properly. carefully take out all the information from the figure as well as a problem, given problem. Take out all the information. This is most important thing. This is where your engineering intuition will be very, not intuition, engineering information. Okay, engineering information will be very useful to define the problem. First of all, before solving the problem, you need to define the problem. So what exactly problem is, that you need to understand first of all, and then you will go for solution. Take down this problem carefully, Roll number 54, Deep Shikha.
Yes, sir.
Have you taken down a problem?
Yes, sir.
Can you read the problem loudly?
The fluid is placed in between the two cup arrangement as shown in the figure, and the outer cup is then made to rotate with a constant angular velocity omega naught. The conditions of measurement are controlled so that there is a steady tangential laminar flow in the annular region between the two coaxial cylinders shown in the figure. Because of the arrangement used, all end effects are negligible. Derive the expressing for theta velocity profile, assuming fluid in the space behave like Newtonian fluid with constant viscosity and density.
Okay. Here the cup arrangement is shown. Okay, two cup arrangement. So this is outer cup. Can you see my arrow? Deepshikha?
Yes, sir.
Okay, so you can see my arrow now properly.
Yes, sir.
So this is outer cup. Okay, so even though this is looking rectangular, okay, from figure, this is the you can assume, okay, if glass is placed in front of you and this is front view of glass, it will be just this line. Okay, so this is say outer cup rectangular, this is not rectangular, this is cylindrical cup. Okay, this is cylindrical cup front view. Okay, this is two cup arrangement, and this is inner cylinder. This is inner cylinder and this is outer cylinder. Okay, this outer cylinder is connected with some shaft here. This outer cylinder is connected with shaft here, and this shaft is rotated with a velocity of omega 0. This is radian per unit time. Radian means, okay, this is, you can say, rotation per unit time, one rotation. Okay, so it will be 2 pi radian. Okay, so sometime can be angular velocity will be in the form of rotation per unit time or radian per unit time. So it is this shaft is rotated with the angular velocity omega 0. So as shown in figure, so outer cup is made to rotate with a constant angular velocity omega 0, and inner cup is steady. This inner cup is steady. This inner cup is not moving at all. Okay, inner cup is not moving at all. The condition controls such that flow is steady. So there is no variation with respect to time, steady state, and tangential laminar flow is there. Tangential laminar flow tangential to this surface. Okay, tangential to this surface flow is there between two coaxial cylinder as shown in figure. Because of this, all end effects are negligible. So derive the expression for v theta, assuming v theta velocity profile, assuming Newtonian, so constant density and viscosity. Roll number 55, Somesh.
Yes, sir.
So which are zero velocity? First of all, which coordinate system you want to use?
Cylindrical, sir.
Cylindrical coordinate system. So as soon as you say cylindrical coordinate system, so this 45 equation boils down to 15 equation, and then you want to use Navier-Stokes equation, because again here also constant density and constant viscosity system. So you can use Navier-Stokes equation. Navier-Stokes equation for cylindrical coordinate system will have three equations. What are these three equations, Somesh?
Sir, Z equation of motion, theta equation of motion, and R equation of motion.
Z equation of change and
Theta and R.
So which equation will give me a velocity profile for this problem?
Theta.
Okay. So what are zero velocities and what are non-zero velocities, Somesh?
So, so it is given that it is constant, so VR equal to 0, like it is steady angular flow, annular.
So why VR equals to 0?
So because it is rotating at constant, like omega is constant.
So, but why VR equals to 0?
That tangential laminar flow.
So that given it is tangential laminar flow, and one more information is given. Because if you look at this region, can you see my arrow, Somesh?
Yes, sir. Yes, sir.
Okay, here VR is not equals to 0 because this is rotating with this fluid, so fluid will try to move in outward direction because of centrifugal force.
Yes, sir.
Okay, this fluid will try to move in outward direction, but we are considering VR equals to 0. Why? Because these are considered as the end effects. So I'm not considering this region for v theta velocity. Here v theta velocity will behave complicated. Okay, this variation of model equation for v theta will depends upon r as well as theta, r as well as z also. Z, everything will be function actually. So this I am accounting as a end effects. Okay, I am not looking into this region. I am looking into only this region. So how v theta is varying in this direction? Here vr equals to 0. Okay, and why what the reason? Because it is given tangential laminar flow. First of all, tangential laminar flow is given. Secondly, end effects are neglected. Whatever be the variation here in this region, that will be neglected. Whatever be the variation here in this region will be neglected. Okay, Somesh, this is
Yes,
clear
sir.
to everybody? Why VR equals to 0? Why VR equals to 0 and Vz equals to 0? Both have same logical explanation. Because it is given tangential laminar flow. Tangential laminar flow, it is given that V theta is dominating. Tangential flow means V theta is dominating. Laminar flow means 1D flow is there. It means that there is only V theta. It is given. And another reason is end effects are also neglected. So there will be VR, VZ, VR, VZ, VR, VZ might be there, but that is there in this region. Okay, that is there in this region, and that end effects are neglected. So which is non-zero? Only V theta is non-zero. Clear? Clear to everybody? This is clear to everybody? Somesh?
Yes, sir.
Somesh?
Yes, sir. Hello?
Yeah. So V theta is a function of R, theta, and Z. So whether V theta is a function of R, theta, and Z, Somesh?
So only R.
Why it is not function of theta?
So, symmetricity.
Problem is symmetric around theta.
Yes, sir.
And why it is not function of Z?
So,
Yeah, anybody else in a class? Why V theta is not function of Z?
Because one end of the cup is closed.
Yeah?
So one end of the cup is closed. That's why it won't be a function of Z. End effects.
It is a function of Z, but we are neglecting. It is not a function of Z. It is a function of R only. Why it is? It can be considered that V theta is not a function of Z. Any logical reasoning for this? end effects are neglected. Again, same thing. Okay, there V theta will be function of Z in this region. This and this is symmetric actually. And it will be function of Z in this region also. Because this surface is rotating, this surface is steady. So as I am moving here, here velocity will be 0, here velocity will be some linear velocity will be 0, here some velocity. So certainly it is function of Z, but end effects are neglected. So I am not looking to derive the equation for V theta for this region. For this region, it will be more complicated actually. So I am just concentrating in this region. Okay, in this region. So I can neglect this region, saying that end effects are neglected. At the end, here there will be some variation of V theta with Z. Here there will be some variation of V theta with respect to Z. Here there will be some variation of V theta with respect to Z. But I am not concentrating in this region. My region of interest is only this. In this region, V theta is function of R only. Hence, I can say that V theta is not function of theta because problem is symmetric around theta. V theta is not function of Z because end effects are neglected. So I am neglecting all end effects. Okay. To simplify the problem, some assumption should be taken. Here I am taking assumption that end effects, negligible end effects, hence can be neglected. So theta equation of change will be important to get the velocity profile. So how many boundary conditions are needed to solve this problem? Roll number 57, Aman. Roll number 57, Aman. Roll number 58, Devang.
Yes, sir. Sir, I guess for theta, for solving V theta will be 2. Like at lambda r, the velocity will be 0, and at r, the V theta will be equal to the angular rotation velocity.
Linear velocity. So here linear velocity will be equals to
omega into at first cylinder it will be 0. At second cylinder it will be omega into r V theta.
Okay. So here velocity will be equals to 0. Okay. At r equals to kappa r. Okay. This is r equals to kappa r. V theta will be equals to 0. And at r equals to capital R, V theta equals to omega naught into r. Okay. This is linear velocity profile. Okay. This is linear velocity. So this is what the information is there from the given problem. This is all information given in a problem. Okay, given in a problem. Once we have this, so as I told, you need to start with all 45 equation. This will be a first step. So out of this 45, these 9 equations are important. Out of these 9 equations, 3 equations which are for cylindrical coordinate, spherical coordinate, cylindrical coordinate, 3 equation, r, theta and z equation of change are important. So out of this 3 equation, theta equation of change for cylindrical coordinate will give me a velocity profile. Okay, this is a 3 equation of change for Cartesian. This will not be useful. This will be useful. This 3 equation of change, and this will not be useful. Okay, this cylindrical coordinate, and this will not be useful. This will give me some other information. Okay, if you pressure is function of r. Pressure is function of r because of centrifugal force, and this pressure is function of z. Pressure is function of z. This is gravitational force. Pressure is a function of gravitational force and centrifugal force. That information is available in this r equation of motion and z equation of motion. But as I want theta velocity profile, v theta velocity profile, this theta equation of motion will give me a velocity profile. So this will give me a velocity profile. So v theta, so vr equals to 0, vz equals to 0. So v theta is a function of r only. V theta is not function of z, because end effects are neglected. V theta is not function of theta because problem is symmetric around theta. Pressure is a function of R and Z. Pressure is a function of R and Z. So R because of centrifugal force and Z because of gravity. Okay, and this information is available in R equation of change and Z equation of change. But for time being, for this in this problem, we are interested in deriving the velocity profile for V theta only. So this information we'll look into in next problem. Actually, next problem when this thing. So boundary condition at R equals to kappa R at this surface. At this surface, the V theta equals to 0, and at R equals to capital R, V theta equals to omega naught into R. So these are the boundary condition. So out of these three equations, so this R equation of change will give me a variation of pressure. So if you see actually, so R equation of change. So one by one you can neglect whatever the zero, non-zero terms actually. So who is next? Aman is over. Devang. Aditya, roll number 60.
Yes, sir. Hello, sir.
Aditya, roll number 60.
Hello, sir. Am I audible?
So can you just talk loudly? I'm not able to hear you properly.
Hello, sir.
Yeah. So this is R equation of motion, which is important when we will be discussing variation of pressure with respect to R. So which is zero, non-zero terms here?
Sir.
This is zero or non-zero?
Sir, del V R by del T is 0.
Why? You can tell zero, non-zero, and reason also with that.
Okay, so first term is 0, steady state. Second term is 0, VR is 0. Third term is a minute, sir. VR. Third term is VR is function. Fourth term is 0. And
Third term, what about this third term?
theta is function. Sir, sir, it will be 0.
Why?
Sir, sir, symmetricity.
VR equals to 0, no?
Hello.
VR equals to 0, na?
Yeah, sir. Yes, sir. Sorry, sir. VR is 0.
So why you need to consider symmetric and non-symmetric if something is 0?
Sorry, sir. I was confused. VR is 0.
What
That's
about
why
this
it's
one?
it will be 0, sir, because VZ is 0. And
VZ is 0. Okay.
And
how about this term?
Which term, sir? V theta square by R is not 0.
Not 0. This will be non-zero. This will be
del P by del R. Sir, pressure is, sir, pressure will be it will be non-zero, sir, because
pressure is a function of R.
R, yes, sir.
So whether this is 0 or non-zero?
Pressure, sir. Sir, it will be non-zero.
Why? Why pressure is a function of R?
Sir, because there is
Why pressure is a function of R? Just now I
sir,
told, na?
sir,
Pressure is a function
due
of
to the force, yes, sir, centrifugal force and gravity.
centrifugal force. Now you assume yourself as a molecule. Okay,
Yes, sir.
and you tie yourself with a length of say rope. Length of rope is 1 meter, and rotate yourself with an angular velocity of omega naught. Now you will be feeling some pressure. Now say a length of the rope is 5 meter and you are rotating with same omega naught velocity.
Yes, sir.
So whether you will be experiencing different pressure or same pressure?
Sir, can you repeat the question, please, sir?
You assume that you are a molecule.
Yes, sir.
Tie yourself with a rope of length 1 meter. Okay. And
then 5 meter. Okay.
You think that you are rotating at the radius of 1 meter with the angular velocity of omega naught. Now you are experiencing some pressure.
Yes, sir.
Now case number 2 is now length of the rope is increased from 1 meter to 5 meter.
Yes, sir.
And again angular velocity is omega naught.
Yes, sir.
So whether you are experiencing same pressure or different pressure?
Sir, it will be different, sir, because
Because of
angular sir,
centrifugal
because
force. That is called
centrifugal
as a
force is
centrifugal
changing.
force.
Yes, sir.
Centrifugal force. Here also pressure on a molecule is a function of R because of centrifugal force.
Centrifugal
So
force.
this is non-zero. Whether this is zero or non-zero?
Sir, it will be 0. VR is 0.
What about this?
Sir, it will also be 0 because del VR by del theta is 0.
VR equals to zero. No? This
Yes,
is
VR is also equal to 0. That's why. This is also
what,
equal to 0.
why?
Sir, VR is 0.
How about this?
And del V theta by del theta, it will also be equal to 0 because
Why?
V theta is only changing in our direction, symmetricity, we can say.
Why it is not changing in theta direction?
Sir, symmetricity.
Very symmetricity. How about this rho into GR?
Sir, GR will be 0.
GR
That's
will be
why.
equal to 0. Only non-zero terms are this and this. Okay.
Yes, sir.
So you can see the R equation of motion will give me a information. What information will give me? It will give me a variation of pressure with respect to R. Okay. So kind of centrifugal force information will be given by R equation of motion. Now similarly, I will go for theta equation of motion. Okay. This is clear to everybody? Okay, what this equation is giving me? This equation is giving me how pressure is changing with respect to R. Going to second equation, theta equation of motion. Who is not next? Who is next? Roll number 57. Aman. Roll number 57, Aman. Are you able to listen to me? Am I audible?
Yes, sir.
Yes, sir, you are audible.
Okay. Aman. Devang. Roll number 58, Devang.
Yes, sir.
So can you explain this theta equation of motion? Simplify this theta equation of motion which is given on a slide.
Sir, V theta by Vt will be 0 as a steady state. Sir, V theta by Vr will be non-zero because theta is varying in our direction, but Vr is 0. So overall equation will be 0. Then V theta into the third term will be 0 as V theta by del V theta by del theta will be 0.
Why? Why? You tell
Sir,
me why
because
also.
okay, sir. Sir, del v theta by del theta will be 0 because v theta is only function of r and not theta because of symmetric flow.
Very good.
Sir, vz will be 0 because of end effect is neglected, and
Very good.
vr is 0.
Okay, this is
So
0.
fifth
So
term
everything is
0.
0 here. Huh? Everything is
Yes,
0.
sir.
So how about this term?
Sir, it will be 0 as pressure is varying in r direction only and not
Why
theta
pressure
direction.
is not function with theta direction? Why pressure is not function of in theta direction?
Because, sir, in theta direction there is no force, so no pressure.
No. Because there is symmetric. Problem is symmetric around theta.
Okay, sir.
Problem is symmetric around theta. So what do you mean by symmetric? Means if you move in theta direction anywhere keeping r and z constant, you will see identical properties because problem is symmetric around theta. Okay. How about
Yes,
this?
sir. Sir, with theta, sir, I think it should be non-zero.
Why?
Sir,
Why
v
you
theta, sir, v theta will vary in r direction. So del
v
into del r.
First of all, v theta is non-zero and v theta is a function of r. Hence, this is non-zero. How about this term?
Sir, it will be also, sir, v theta by del square v theta into del theta will be zero, as v theta is only varying in r direction.
How about this?
Sir, it will be also 0 as v theta is only varying in r direction and not in z direction.
Why v theta is not function of z direction?
Sir, also end effects are neglected.
Very good, very good. How? What about this?
Sir, VR is 0, so term is 0.
How about this?
Sir, 0 as
Why?
g theta is 0.
Okay, this is theta direction is perpendicular to this. So this is vertical. Okay, r direction. Okay, this is z direction. Okay, gravitational force is in negative z direction. If I consider origin here, negative z direction. So this will be 0 actually. So this is the equation which will give me, if I solve this equation, I will be needing two boundary conditions and will be getting a velocity profile. Okay. And now I will go to third equation of motion, Z equation of motion, and see what information I can get from this equation of motion. So is next Aditya, roll number 60.
Yes, sir.
Yeah. Can you simplify this equation?
Yes, sir. Del Vz by del t is 0. Because steady state. Then second term is Vr is 0. That's why second term is
Very
0.
good.
Third term del Vz by del theta is 0 because symmetricity. Oh no, Vz is 0.
Vz by del theta equals to 0, not because of symmetry,
So
because
Vz is
Vz
0.
equals
0. Yes, sir. Then fourth term Vz is 0. That's why the term is 0. So whole LHS is
Okay.
0. Then del P by del Z is non-zero because pressure is function of R
Because
and Z.
pressure is changing in Z direction because of
Yes.
gravity.
Yes,
Okay.
sir. Then del Vz by del R, del Vz by del R is 0 because Vz is 0.
Very good.
Then del square Vz is 0. Vz is 0, that's why that term is 0. And
Very good.
Vz is 0, that's why third term also 0. And
How about this?
Gz is non-zero, so it will remain.
GZ, what will be GZ equals to? Here
Gz
you
will
can
be
see origin is considered here.
minus.
Z direction is, what will be GZ will be equals to?
Minus G.
GZ will be equals to minus G. So substituting GZ equals to minus G. So this is the equation. Z equation of motion is giving me variation of pressure in Z direction. how pressure is varying in Z direction. So pressure is function of R because of gravitational force. Okay, that is what I was telling. Pressure is function of Z because of gravitational force. Pressure is function of R because of centrifugal force. Okay, so these are the three simplified equations. So first R equation of motion, R component will give me variation of pressure with respect to R. Z component will give me variation of pressure with respect to Z, and theta component will give me a velocity profile. Once I have velocity profile, I can discuss the variation with respect to R, and this is variation with respect to Z. Now I want a velocity profile. So to get the velocity profile, I will solve this theta component using these two boundary conditions. Okay, solve this equation. So solve this equation, integrate this equation twice, and substitute this boundary condition. Okay, so you will be getting a velocity profile for a given problem. That is what we need. Velocity profiles. Integrate this equation twice. Integrate this equation twice and substitute this two boundary condition and get the velocity profile equation. So integrate this theta component twice because there are double differential. Okay, double difference. This is differential and this is differential. So integrate this equation twice and substitute these two boundary conditions to get the constant of integration. Two constant of integration. Yeah, roll number 62, Rameshri.
Yes, sir.
What you will get after integrating first integration?
Sir, we get 1 by r into t
1 by r into
t by tr of r v theta equal to
that
c1.
will be equal to
c1.
C1. Okay, and then you can now shift the r.
R to
Rearrange the r, then integrate, again integrate.
yes, sir. So we get r v theta equals to half c1 r square plus c2. By rearranging, we get profile equation is v theta equals to half c1r plus c2 by r.
Okay, now you have two constant and two boundary condition. At r equals to kappa r, v theta equals to 0. At r equals to capital R, v theta equals to omega naught into r.
Yes, sir.
Substitute this. So everybody is getting this. V theta equals to half C1 R plus C2 divided by R. Everybody is getting this equation. Anybody not getting this equation? V theta equals to half C1 into R plus C2 divided by R. Now if I substitute kappa R here, V theta equals to 0. V theta equals to 0 and capital R, V theta equals to omega naught into R. Substitute this and get this value of C1 and C2. And rearrange the equation. So solve this equation V theta, get the value of C1 and C2 using these two boundary conditions. Roll number 63, Shreyas.
Hello, sir. Am I audible?
Yeah, you are audible. What is the value of C1?
Sir, I'm finding, sir. 2 minutes, sir.
Yeah, Shreyas Kulkarni.
So 1 minute, sir.
Anybody got the value of C1?
Yes, sir.
Who got it? Can you tell me your roll number?
Sir, 60.
60. Yeah, can you tell me C1? What is the value of C1?
Minus 2 sigma by k square minus 1.
Sigma 0, na? Sigma 0.
C1, sir. Sigma 0. Yes, sir. Sorry.
Okay, and how about C2?
C2 is k square sigma 0 r square by k square minus 1.
So, so these are the boundary condition. And substituting this, you should be getting this velocity profile. Substitute C1 and C2 and rearrange the equation. So, what is the main strategy we will apply for rearrangement so that I will get back this boundary condition very easily. So rearrange, substitute this value of C1 and C2 and rearrange the equation. So you will be getting this velocity profile equation. Now see, R equals to kappa R. So here I will substitute R equals to kappa R. So kappa R divided by kappa R. This here also I will get kappa R divided by kappa R. 1 minus 1 will be equals to 0 and V theta will be equals to 0. At R equals to R, capital R. This capital R will be there. Here I will get 1 by kappa. If I use here R, 1 by kappa minus kappa. So 1 by kappa minus kappa divided by 1 by kappa minus kappa, this will be equals to 1. So V theta equals to omega naught into R. So both the boundary condition I can get very easily. So how many of you are getting this C1, C2, value of C1 and C2 and this velocity profile? You can write in chat box. How many of you are getting this velocity profile equation? Got it, got it, got it. Okay then, thank you very much. If you have any difficulty in today's class, just
Excuse me, sir.
let me know. Otherwise, we will continue case number 2. Some few cases for this problem itself in next class.
Excuse me, sir. Am I audible?
Yeah, tell me. Yeah.
Sir,
Roll
while
number?
discussing, sir, 4, Aditya.
4. Yeah, tell me.
Sir, while discussing the V theta as a function of Z, you said that we should consider the end effects are neglected. But can we state another reason? Like we know that the outer curve is moving with certain velocity, angular velocity, and it is given that there is tangential laminar flow, and both words are important. So, can we say that the molecules inside the area, the molecules are moving with such frequency of velocity that they have overcome the gravitational force, like the velocity. That velocity has overcome the gravitational force. That's why it is not varying with Z direction.
No. But if you see now, can you see my cursor?
Yes, sir.
Okay. Now say I am here. My molecule is here.
Yes.
Okay. What will be the velocity of this molecule?
Sir, at the end, sir, it will
here.
have V theta velocity only.
Yeah, V theta velocity, some value of R into V omega naught.
Yes, sir.
Okay. Now I am just moving in Z direction. Just moving in Z direction. And I am at this point.
Yes,
what
sir.
will be my velocity?
So again, it will be only R. It will be only function of R, not Z.
No. Here at this surface, where is my cursor now?
Yes, sir.
At this bottom of this upper cup.
So then, because of no slip, it will be no. Yeah,
So
yes.
here velocity is omega naught into R. Here velocity is 0 and I am moving in only Z direction.
Yes, sir.
So V theta is function of Z in this region.
Okay.
You assume whatever you want to assume, but V theta will be the function of Z in this region.
Yes, sir. Yes, sir. Got
Similarly,
it.
here also, this top layer of the fluid, there is a fluid in between this cavity. Top layer of the fluid is experiencing, you can say, gas here, or whatever be the phase here, gas phase here. But here molecule is experiencing liquid on all the sides. So certainly pressure on the molecule will be different here as compared to this. Here also there will be small variation in V theta with respect to Z when I am moving in Z direction. Okay.
Yes, sir.
So in this region, so this is symmetric in this region, and in this region, V theta will be the function of Z. But as this is my region of interest, this is my main region of interest where I want to develop velocity profile. Hence, I am neglecting this variation here. I am neglecting this variation here and accounting these as the end effects.
Yes, sir.
Okay.
Yes, sir. Got it. Thank you.
Okay. Okay.
Excuse me, sir.
Everybody is getting. Yeah, tell me. Roll number.
No, sir. Actually, I don't have a doubt. Sir, I just wanted to ask you, could you please share the attendance sheet of our batch, as most of us will be traveling in the next weeks to come to the campus, so we can schedule it accordingly so that least of our attendance is missed.
Oh, so you want to attend according as your attendance is there. If your attendance is 100%, so you will be
No,
escaping
no,
some
sir.
of the classes.
No, sir,
You will be
that's not.
absenting.
The thing is that already most of us have booked the tickets, but like if attendance is short, then we have to cancel it and reschedule it.
Okay. Okay, I will share on Monday.
Thank you, sir.
Okay, anybody else has any doubt? Okay, then thank you very much. We'll continue this discussion in next class actually. There is couple of cases for same problem.